Hello viewers, welcome to Homogeneous tutorials. I am Sir Amos, and today we are going to look at solutions to the non-separable ordinary differential equations, also known as the Euler homogeneous equations. Now, in our previous lesson, we learned about the separable ordinary differential equations. That was the previous video I posted. Our lesson was about the separable ordinary differential equations of first order. So when we said that if I have an equation such as e raised to the power x y prime is equal to 1 over y, this equation can be separated or is separable. And to solve this equation, what we do is we multiply both sides by y. So we have y e raised to the power x y prime is equal to 1, and then we divide both sides by e raised to the power x. So we have y prime is equal to e raised to the power 1 dividing e raised to the power x. So the next time we do is to change the y prime into dy dx. So we have y dy dx to be equal to e raised to the power negative x. That is by sending the e raised to the power x to the top. So the power becomes negative. And so we have y dy to be equal to e raised to the power negative x dx. And then when we do this, we have been able to separate the variables. So we take the integral of both sides with respect to each of the variables, and then we solve it. So these were the types of equations we did, which we call them the separable ordinary differential equations. So by the separable equations, we learned that those equations, the dependent and the independent variables, can be separated to both sides of the equal sign, as we just demonstrated. Now, we have certain types of equations that when you study the equation, you realize that it's not possible to separate the variables. For instance, if I have x y prime to be equal to x plus y, looking at this equation, we cannot separate it. If I want to separate the variables, I will divide by x, divide by x, and I'm going to get what? Y prime to be equal to x over x plus y over x, and y prime to be equal to 1 plus y over x. So looking at this, you realize that it is not practically possible to separate the variables. So we call this type of equation the non-separable ordinary differential equation. So to solve this particular equation, what we do is we try to reduce the equation from the non-separable form into a separable form. And so by doing that, we'll be able to integrate both sides with respect to the various variables. So we are going to take the steps or the procedure that is involved in solving the non-separable ordinary differential equation. Okay, so the Euler homogeneous equation is of the form y prime to be equal to f of y over x. So when you look at the form like this, the non-separable ODE has this form. So when you look at the form, you see that the y over x is inside the function. So that makes it not possible to separate the variables. How then do we solve this? As I said, we solve this by reducing it from the non-separable form into a separable form. So that's by reduction method. And then we try to change the dependent variable into a new variable so that we can integrate both sides. So we say that let u to be equal to y over x. So if u is equal to y over x, then we have to so that we make y the subject from this one, and we have y to be equal to u times x. So if y is equal to u times x, that is from here, then we can differentiate y. So differentiating y here will give us the derivative of y to be equal to what? Differentiating u and maintaining x plus maintaining u and then differentiating x. Here we have applied the product rule. We have a function u multiplied another function x. So by the product rule, we are going to have what? Y prime to be equal to what? We first differentiate x, u. We first differentiate u and maintain x. Then we add it to second maintaining u and differentiating x. When we differentiate the u, we are going to get u prime. Why? Because the u is a function of y over x. It's not just a variable. The u has something inside it. So its derivative will not give you 1. But rather, we have to put the derivative sign on top of it. But when we differentiate the x, we are going to get 1 because the x is just what? A variable. So, having done this, we can label this as equation 1. And this becomes equation 1. And we label this as plus u as equation 2. The next step is to put equation 1. We put equation 2 into equation 1. That is, wherever we see y prime in equation 1, we put u prime x plus u there. So the equation 1 therefore becomes what? We have y prime, that is now this. So this becomes u prime of x plus u. Then to be equal to what? F of y over x. But y over x was u, so this becomes f of what? U. Now we have changed the dependent variable into a new variable u, and the function is now in terms of what? X and u. So the next step is to group like terms and then separate the variables. So we have u prime x to be equal to f of u minus u, and then we have what? U prime x. So now we can change the u prime into du dx. So here becomes du dx multiplying x to be equal to f of what? U minus u. So we have x du to be equal to f of u minus u all multiplying dx. Now when you look at this critically, you realize that the u's are at this side whilst the x is also at this side. So we can divide both sides by f of u minus u and divide here by x and here by x so that we can send the x to this side and then bring the u's to this side. So by doing that, we have 1 over f of u minus u, then du to equal to 1 over x, then x. So finally, we have succeeded in reducing it from a non-separable form into a separable form. And then the next thing we do is to take the integral of both sides. We integrate both sides with respect to u, and then we integrate here with respect to x. So plus the constant of integration c. So when we do this, then we have reduced the equation from the non-separable form into a separable form, and then we can solve it as we already know. So this is basically the key steps involved in what? Solving the non-separable or the either homogeneous equations of first order. So we want to take an example and then we see how we can apply these procedures in solving the non-separable ordinary differential equations. The first example says that find a solution to xy prime to be equal to x plus y. Xy prime to be equal to x plus y. So we have the equation given to us as x be equal to x plus y. So when we see the equation like this, the first attempt is to try separating the variables. But when you look at this equation, it is not possible to separate the variables. So what we do is, we first of all make y prime the subject. So I have y prime to be equal to x plus y over x. That is by dividing both sides by x. So my y prime will be equal to x over x plus y over x. And so I have y prime to be equal to 1 plus y over x. Now, at this point, I have been able to write the equation into its standard form. So we have y over x there. The first step is to what? Let u to be equal to y over x. I'm using u. Another person can use v. You can also use any other variable which you deem necessary. So using u to be equal to y over x, then so that we have y to be equal to u times x. So that is making y the subject from here. And then differentiating y, we are going to obtain the derivative of y from here to be equal to first differentiating u and maintaining x, then second differentiating x and maintaining u. So when we differentiate x, we will get 1. 1 times u will give us u. Alright. So the next step is to what? To put this particular equation into the first one that we obtained. So I can represent this as equation 1, and then this becomes equation 2. So I put what? Put equation 2 into equation 1. So by doing that, when we write equation 1, wherever we see y prime, we put u prime x plus u. And so equation 1 becomes what? Becomes u prime x plus u to be equal to 1 plus y over y. 1 plus y. But y over x, we said should be equal to what? U. So this becomes 1 plus u. 1 plus u. So we group like terms now. We have x prime to equal to 1 plus u minus u. And so we have u prime of x to equal to what? 1. U minus u will give us 0. And so we change the u prime into du dx. So this is the derivative of u with respect to x. So we have x du dx to be equal to 1. And so I can multiply both sides by dx, and I'll have x du to be equal to what? Dx. 1 times dx will give us dx. So the next thing to do is to what? To regroup. So at this point, the equation has become separable, and we are now trying to separate the variables in terms of u and x. So I divide both sides by x, and I will obtain du to be equal to 1 over x dx. So integrating both sides, so I integrate this side with respect to u, and then I integrate this side 1 over x with respect to x. Integrating 1 with respect to u will give us u, and integrating 1 over x will give us ln x, then plus the constant of integration c. Now, how did we get u here? We learned that if I differentiate x, I'll get 1. So if I integrate 1 with respect to x, I'm supposed to come back to what? X. In the same way, if I integrate 1 with respect to u, I will get u. But we know that u was equal to y over x. From our previous workings, u was equal to y over x. So that means that we can substitute this u by y over x. So therefore we have y over x to equal to then x plus c. And multiply both sides by x, we have hence y, which is equal to x then x plus c. X is the general solution to the ODE. So, dear viewers, we have this to be our solution to the non-separable ordinary differential equation. So these are the steps, the basic steps that are involved in solving ordinary differential equations. So I have more videos on more examples. I have more examples loaded to my YouTube channel. Kindly watch this video, share and subscribe to my YouTube channel to have access or to enable you watch the other videos. Or better still, you can go to my YouTube channel, Homogeneous tutorials, to watch more examples solved under the non-separable ordinary differential equations. Thank you.